Welcome everyone to the second edition of the Phipps-Langlois Geography Seminar Series. Today we are very pleased to have Dr. Vern Singhroy, who is an internationally recognized expert on radar remote sensing applications. He's an engineer. I published over 250 papers in scientific journals, proceedings, and books. He actually just retired from his role as chief scientist at the Canadian Centre for Remote Sensing. And he was part of the team that worked on the Radarsat Constellation Mission, which was launched in June 2019. And today he's here to talk to us about this satellite mission and the opportunities it represents for infrastructure monitoring. So I'm gonna now give the floor to Dr. Singhroy, and we should have enough time at the end for questions, which you will be able to ask either through the chat or using your microphone. So, Dr. Singhroy, the floor is yours.
Thank you, Roxanne. I got roped into this by Anders, who I think is in the audience, yes, to make this presentation. And I'm happy to do this because it's nice and fresh in my mind. Just retired from CCRS and the Radarsat Constellation Mission. What I plan to do, basically, I was told this is 1 hour, so to fill it up, I give you 40 slides, a minute per slide, hopefully, and then we'll have some fun and questions and so forth. I want to give you a little bit of background, and I assume that there's a lot of you who do not know a lot about the Radarsat Constellation Mission. So I'll go into some basics, and then I'll talk about some opportunities, focusing mainly on the geography of infrastructure and mainly monitoring. Basically, the Radarsat program, this is the context. The second question on second part of the chapter, so to speak, is the InSAR basics. And I want to deal with a term called interferometry because we need to talk about how we're going to move forward and what these satellites can produce that is new. So I'll give you some fundamental of interferometry and then apply that to infrastructure monitoring and end up with future directions and those kinds of things. Okay, the big picture is I need to take you back, and forgive me if some of you are experts on radar and the Canadian program, but this is probably not meant for you. So these slides that are Radar 101. And as Canadians, you obviously need to know this. We launched 3 satellites, Radarsat 1, Radarsat 2, and then last year, 2019, in June, we launched a constellation mission of 3 satellites, where I was the chief scientist for this program. So the big picture is back in 1995, Radarsat was launched. Radarsat 1 was launched, and it died, so to speak, in 2013. A very long history and providing us with a lot of radar imagery. We'll talk a little bit about that, but basically radar looks to the side in all these missions, and you will see the application there, unlike the optical sensors, which look down. The slide is meant to show you that you can order different modes of data from the government of Canada and industry in some cases. These images has swath width. In some cases, you can have 100 kilometers, other areas 45, and in the case of RCM, you can have 500 kilometers of swath width of data over the ocean. And if you're looking over the city, you can have a 5-kilometer swath width over the high resolution. So it shows the swath width, it shows the resolution. Again, in the case of RCM, called a spotlight mode, you can have a 1 meter resolution at a 5 kilometer swath width over Ottawa, let's say. So this is just a general table that gives you the characteristics of these 3 satellites. Radarsat 1 does not exist, Radarsat 2 does exist, and Radarsat 3. So currently you could get imagery from these two satellites. Okay, this is the big picture. To show you that we're not the only one. Canada is not the only country that has radar satellites. There are other countries. We have Radarsat 2 and the Radarsat Constellation. Just to give you some background, it's these satellites belong, so to speak, run by the Canadian Space Agency. They're the agency that is responsible for the engineering, and you have government departments develop the applications in collaboration with CSA. The dates these satellites were launched, and some characteristics about the frequency. We'll get to that later on if I'm getting too much in the weeds. C-band, X-band, L-band, and so forth. The frequency, the wavelengths, the polarization, the incidence angle, the resolution, the swath width, how fast they look at an area, repeat, 24 days as opposed to 1 day, and so forth. We'll get into all this, but the purpose of this table is to give you who is out there and what they're all doing in the sense of their payloads. So Canada, we're not the only one in the radar business. And just to give you an idea, the German Space Agency called TerraSAR and TerraSAR-X, they have certain characteristics of their satellite. They're a little different from ours, but we share the same frequency in some others, in the sense of the European Space Agency. The German has an X-band. We will deal with that. It shows the if you like, the frequency, the band, and the centimeter in the sense of its wavelength. Moving forward, without going to the weeds again, moving forward, the Japanese, their satellite is called ALOS, their radar satellite. The Italians, Cosmos SkyMed, Italian Space Agency, Sentinel A1, the European Space Agency. And over here you have the new folks. India and NASA is putting up their first commercial satellite. They have also military radar. And NASA and ISRO, Indian Space Agency, to be launched 2022. Capella Space, a small company in California, Palo Alto, California. They have a small one up there. They just put up another one the other day. From Finland, you have ICE. Then you have the South Koreans, and others are in the business of Radarsat. So the industry looks good. It's growing. A lot of new science to work with all these geophysical parameters of radar. From the bandwidth, they change. The viewing geometry changes. The polarization changes, and so forth. So we need to sort it all out, the students, the young students, professors and scientists and so forth, to sort this all out for application. Okay, for the uninitiated, the one who is, what is SAR and what does it do? Radar is, SAR stands for synthetic aperture radar. You need to know, and this is again Radar 101, you need to know it's an active system. It uses a transmitter to illuminate the scene. The pulses are sent in microwaves. This is very critical because the microwave, we speak of radar backscatter, and we'll get to that in a little bit. And some of the physics of it we need to know is the amplitude, the phase, some physics, a type of frequency, and the scatter, the polymetric scatter. As I talk about application, we will understand this in a little more detail. Radar records the backscatter. Unlike, again, sunshine, it has its own light, so to speak, its own energy. I tend to simplify these things if it's by saying it has its own energy. Radar does not suffer from cloud cover or fog or day or night because it's like a flashlight from space. Pardon my term flashlight, but it's making a point, however. A radar flashlight from space. Radar systems using remote sensing are usually mounted on aircraft. We have some industry that provide airborne radar. They actually started in Canada. The big one is in the United States now, and provide a lot of airborne data for the military and so forth. NASA JPL, we at CCRS usually have a aircraft radar for many, many years before we have our satellite. And Canada is known internationally. We have been in this business for a long time. When I joined CCRS in 1990, we had an airborne aircraft, airborne radar. So we've been doing well, and 30 years ago, and now we're doing fairly well. We got a lot of satellites up in space. Okay, a little detail before we go into the application. For some of you who don't know anything about radar, if this is a spacecraft or an aircraft, it sends the energy down. The radar is transmitted to the ground. It backscattered, and the backscatter is a function of the target. If it's water, then it scatters all over. If it's like a city, it goes, a lot of the energy goes back to the antenna, to the receiver. So the energy is scattered in all directions, if in the case if it's an ocean. A small part of the energy is scattered back to the radar, and that's where your signal comes from. That's where you analyze all the data, the information for application. This one, I put it in because it deals with what we may call a polarization. From some of you, there's no, it vibrates in, or it sends out in horizontal, HH, VV, and vertical, sends and receive. And in the case of RCM, one of the things we introduce is a circular polarization, and we'll get into that a little later. So the backscatter is very important when we deal with interpretation. Okay, a little bit more on the context and Canadian radar program, Radarsat 1, 1995 to 2013. Radarsat 2 still flying. RCM just went up in 2019. A little bit about the technology. The satellites are very big, 2750 kilograms. And as we move forward, it's getting very smaller, and that's why we're putting up more constellation. In the case of the new radar satellites, like Capella Space, they have very small satellite, but does not have all the polarization. They're less complex. So if you want to do very, very interesting science and understanding processes and targets, you need to have fairly complex scatter. The smaller satellites, because their functionality are very limited and they're very smaller. The engineering is less complex. Revisit nowadays, we're getting to 4 days in the sense of RCM. In our case, the RCM, the satellite is lower. These were very higher, 800 kilometers. The antenna size is smaller, getting smaller. The polymetric scatter are getting more complex. Hence, there's a lot of new science to be done as we look at these target and different polymetric scatters. And the radar always looks to the right. And in our case, it's owned by the government. The Radarsat 2 is owned by the industry and government. It's still owned by the industry and government. Okay, some little notes on about RCM, since the talk is about RCM, Radarsat Constellation Mission. Okay, average daily revisit. Now we're watching Canada or anywhere in the world every day, not at the same angle, different angles, that's why every day. 90% of the globe is covered, so we have a good footprint and we can help various countries apart from our own. And a lot of this is being done with Department of external affairs, I think they're called, on how much data we give to the other countries. The science now in the area that I'm interested in, the 4-day interferometric revisit as opposed to 24 days. We'll get into that because this is new science, what we call the science of coherent change detection. These are a mouthful, but I guess we'll get into that a little later. What is new about RCM is this circular polymetric scatter. Instead of looking at a target in a linear way, vertical, vertical, horizontal, horizontal, we can look at it in a circular way, and therefore our physics of backscatter changes, and therefore interpretation changes and information changes. So it's a very exciting time for radar. We also, because we're a country that we're very good at the ocean application and ship detections and so forth, relative to the rest of the world, we have a secondary payload on board. It's called the Automatic Identification System, AIS, for ship detection and identification. So this is very new, and we're the first actually in the radar business, apart from the Europeans are doing it now, to put this in our radar, and therefore we can do our satellites, so we can do far more identification. Okay, a little bit about who gets the data and what a policy is all about. From the acquisition point of view, there's no commercial tasking. The satellite belongs to the government, owned by the government, and the government decides who gets it. You cannot sell the data. If industry wants it, they have to go through again through the government system. Unlike the Radarsat 2, which was owned by the government and Canada. Acquisition plans, it can be over the large areas on various areas, various imaging modes, and various coverages in different frequencies in our case. No commercial data distribution. You need to be registered with the government of Canada in the case of CCRS or the Canadian Space Agency before you have access. And each company or academic or what have you, you need to be vetted before you've been approved. The data, again, ownership of RCM data remains with the government of Canada. However, the value-added products, the methodology from the professors and so forth, or the private industry, obviously, your intellectual property belongs to you. There, you need to sign a license agreement with the government and be vetted before you get the data. So for academics and for industry, the data does exist. You can get access to it once you go through the various channels. Another thing you should know, access, if you're looking for data, you can get all this data for free, so to speak, being vetted. And this is called standard coverage. The standard coverage was, I was involved with this for quite a while. What we did when I was at CCRS, we went out to the user, many of the government users, and to some extent our international partners in Europe. And we asked them, it says, what data would you like to collect and why? And Agriculture Canada comes and says, we would like to look at all our agricultural areas at this time of the year with that view and geometry and so forth. And we tasked the satellite to do what Agriculture Canada wants, what the folks from the Canadian Ice Service requires, what the folks from the Canadian Fisheries and Ocean requires, and to some extent what ESA requires. So these are standard covered image coverage by our users, the government users, and that you can have access to when you go through the government. And you can get access to 50 meters to medium resolution, different polarization, and some high resolution data, and every 3 days and so forth. So that data is in the archive collected based on what the users require, and you can have access once you talk to these folks. So that's a standard coverage. Now, the question is, what's next? In my opinion, we require a lot of highly qualified personnel to use these new physics and the new data. apart from the industry folks who are doing the more operational question. So there's a lot of research to be done. Who are the Canadian users? Industry, non-federal government scientists and users, and obviously university folks. Standard covered images are acquired by the government of Canada through and you can get it through CCRS system. No cost, except, and you have to be vetted for security reason, for privacy reason, and for government confidentiality reasons. Okay, how the data is acquired? We have 3 receiving stations in Canada, one in Inuvik, one in Prince Albert, Saskatchewan, and one in Gatineau, Quebec. And these collect the data and corrected it in somewhat, and then we and CCRS and others does the application, or the government affairs, government departments. The reason I put this in is that some of you in Ottawa here, it's a beautiful place to visit in Cantley and Gatineau, especially in the fall. This is one of our receiving station, and they do offer tours. So it's a good thing to go for a tour. Or Anders, you can take your students there at some point for a nice tour, and tells you how the data is collected and how they process it, so it can get to you as a professor or as an industry or government. So I put this in because I'm promoting the tourist version of the Gatineau station. It's easy to get at, and I recommend the fall season. Okay, that's the future, my friends. These are all the application of radar, and particularly RCM. That's where the research is going to be done. That's where industry is going to provide value-added data. And the professors and academia would do research with their grad students and teach courses and that kind of thing. A lot of work to be done on ice, mapping icebergs, looking at the ice data, ice dynamics, very important to the melting, the movement, the characterization. And I think Ottawa U is one of the center of excellence in ice dynamics and the whole radar application and other application of ice vis-a-vis climate change. A lot of work on oil slicks along the ocean, and so forth that's going on in pollution in the ocean. We have a lot of work to be done there, and it's being done currently with those people that are responsible in the government for that. Winds and as it relates to many aspects, shipping and so forth, and characterization, new science, Arctic coastline, Arctic mapping, wetlands, land surface. This is an area I'm very much interested in geohazard, and using interferometry, industry and value-added products, mapping, flooding, geohazard and InSAR, maritime surveillance, and for sure a lot of good advanced work has been done in agriculture in Canada in identifying crops, particularly for radar soil moisture. So this is the future, and it's a mouthful, but I think we need to develop far more smarter people to do these things. That's a similar type of thing I've mentioned in the earlier slide, detail and how I go into detail crop type, forestry, forest types, oceanography, ice, and so forth. And what this table gives you is some of the application which has been realized by Radarsat 1, some of the current value-added products and research from Radarsat 2. And this is where my contribution, this was an old table, so to speak. I've added what I see are some of the future of RCM that is actually going on now. The pluses show some examples, and the minuses so that we cannot do this kind of work because Radarsat RCM cannot is not useful in those applications. So basically, this is a summary of how I see the data in the future, now and in the future. Okay, let's move into what I'm here for, to talk about infrastructure and radar. And I will look at some of these parameters, from buildings to dikes to mining to flood, bridge location and bridge motion, construction, and so forth, as it relates to radar and RCM. Other applications can be used, like drone, LiDAR, stereo photographs, and high resolution images are also useful. The future is the integration of all these data selectively, whenever possibly, with motion data, data from scatter, data from reflectance, data from scatter, data from drone, and data from stereo. When you put these models together, these images together, or selectively, you're moving forward in this day. Okay, Radarsat interferometry, the mouthful of interferometry. What is InSAR? InSAR now requires two imagery or more. Two or more satellites images of a particular area with the same viewing geometry. This is critical. You've got to look at the terrain at the same angle. You cannot look at this, let's say this rock types at a 30 degree and a 40 degree and do interferometry. You have to get a 30 degree first, a 30 degree second, a 30 degree and so on and on. So all you have changes is the phase difference, viewing geometry, all things being equal. The phase difference of the two or more imagery are obtained, and you can obtain the geophysical parameters of height or motion. And that's where a lot of the work is being done, particularly for infrastructure. Now, what we call the time series analysis, and this has been going on in climate change. In the case of radar, time series images or analysis of data has emerged as an important tool for monitoring, and in this case, Earth motion, to understand the geophysical parameters, particularly in the high Arctic, northern Canada, and for infrastructure. I took this slide from the NASA JPL because it just extends what I'm saying here, is that the first satellite gives you a scatter from the first wave. The second satellite gives, if nothing moves, the waves is the same. If something moves on the ground, the waves are different, and therefore you have a phase change. And this is what you measure. And therefore, that's basically interferometry 101 at that level. In the case of radar interferometry, the groundwater were seeping into the land along Long Beach, California. Remember, this is a JPL example, and the ground swells, and therefore they were looking at a 5 millimeters per year of swelling along this area. That's an example. I will show you other examples over Canada. Okay, our first example. So now I'm going to the application part of infrastructure, which is the main reason for this lecture of radar and infrastructure. Hurricane Irene, a couple of years ago, quite a while ago, dumped a lot of moisture in eastern Canada. And in the case of this area, we have a lot of the slopes were saturated and landslides, and the lands are sliding on this highway, and we were able to measure it. And we watched that ground, which is the main landslide affecting the infrastructure, which is the purpose of this slide, to show a time series in the case of May 2009, as far as November 2011, just to give you a snapshot. We're still looking at these slopes with the folks from Corner Brook, Newfoundland, and the Geological Survey of Newfoundland, just to look at time series to see how these slopes are moving. And so they can provide this, Department of Highways can provide these mitigation procedures that they use. Because when this thing, when the slope moves, it blocks the highway 2 or 3 days. They have to clean the mess up, and then you'll have goods and services start to flow again. So just from a science point of view, just to give you on time series from using interferometry, we can look at the motion in May. The land moves a little bit, all these slopes, A, B, and C, moves a little bit, and then the ground sleeps for a while. That's in the November, February, March time, where the ground sleeps. Things are frozen. The spring comes on, melts, summer rainfall, triggers new saturated slopes with a viewing geometry of the radar and a very conducive or say favorable geological conditions, thin soil, thin fill over bedrock. It's conducive, the conducive geological condition, it moves. So the land sleeps in the winter, moves again in the spring, and it continues that cyclical. It moves and melts and frozen, moves and melts and so forth. So these needs to be watched carefully in various parts of Canada, along our whether you're dealing with the Rockies, parts of Quebec, I'll show you, parts of Newfoundland, and even Nova Scotia, parts of New Brunswick. The highway engineers and the geological surveys are starting to use interferometry to supplement some of their ground visitation and some of the ground techniques. A very important use of interferometry for highways. Another example on the oil patch, just to give you just a few examples, just to give you an indication. When steam is injected, this in the case of what is called SAGD, steam-assisted drainage, gravity drainage, the way we extract the heavy oil in Alberta. Steam is injected into the upper well to reduce the viscosity of the heavy oil. Oil produced from the lower well being sucked up because the viscosity is lower. The injection of steam causes a pressure change and a temperature change in here. And that produces, when this thing swells, this is just a caricature, when this swells, the ground swells. And what happens, and it has happened in Alberta quite a bit actually, there was, I think, 1 or 2 fatalities a couple of years ago. So when this swells, so to speak, I'm sorry to use the word swell, when it expands, the ground above it swells, so to speak, and it has what is called a blowout. And the blowout can cause fatality. So in order to watch that whole process of swelling and shrinking based on steam injection, we use interferometry to look at it over time in a time series. And that's plugged into the models with the oil sands folks to do very precise monitoring. Now, make a long story short, this is an example, the red areas, and these are all the pipes underground, which represents this in here. So all these, in this particular area, we have deformation, and we watch these things weekly and monthly and daily, and you have these graph that shows the amount of steam injected and the amount of the trend of where we have the swelling occurs, what they call the deformation. Long story short is the red shows swelling, which can be monitored frequently through interferometry as related to this infrastructure. And as you fill these tailing ponds in Alberta, the soil still behaves like a sponge, and some of it, if you like, swells a little bit for different reasons, and some subsides. So you need to watch all of these as compaction occurs in that whole mining process. You need to watch these as the ground swells and as you extract oil and bitumen from the ground. And these are fairly routine now. The mining companies use this. They're fairly routine nowadays for mining and the extraction of oil in the case of Alberta. Okay, there was a large oil spill a couple of years ago. And Nexon is a company, it was done at the Nexon property, and the red is here, it's just a small area where the Nexon were all these areas where they were extracting oil. And not too far away where they're extracting oil, there was a big bog, a fen. And what we noticed in this bog, and this fen, so to speak, is that the ground was going down more and more and more. And over time, it caused stress on the pipeline, and the pipeline burst. and create the spill. And that's the short story. So all this is telling you is that the InSAR over time, and you can go on and on until 2021, but this gives you a slice, a snapshot of 2008, 2017 of how the InSAR, how the ground is sinking and how the ground is moving over the red areas. At the end of the day, Nexon did a study by consultants, and basically the account says the root cause of the rupture was a thermally driven up buckling of the pipeline because of the heat, of course, that's within this pipeline. And the pipeline needs to be designed better in compatible design, to be designed better for the muskeg condition, which goes up and down in any case on a normal seasonal, but it even go further because of the heat and freeze-thaw process. So the design needs to be changed, and this is what InSAR helps in understanding that process. Okay, pipeline's a big deal for us, as you know, in Canada. In this case, we have a pipeline, Northern Gateway Pipeline, and the geologic. We work with this. We at CCRS work with this, with the Geological Survey, and what the GSC folks are doing, and the geographers and geomorphologists are doing. They watch these land motion, landslides. They're driven by freeze-thaw processes. When the ground swell, when the melt occurs, and the freezing and the thawing, the boulders start to run down in these areas. You have a mini landslide in here in this case, and we watch it over time, the triggering and the accumulation. And because why this is important, it can impact the pipeline. A lot of this kind of studies is going on now with the current pipeline that's being built. Sticking on pipeline, and a long time ago, when I was working for the Mackenzie Valley Pipeline, it wasn't built for a number of reasons. But this just gives you a snapshot of the freeze thawing of the ground. I know a lot of people from Ottawa U, geography, geology, and so forth, environmental, working on permafrost. Well, this is just a snapshot to show how dynamic that whole permafrost environment is. All this is telling you is that the red area is where the ground swells and the blue area is where the ground sinks. And if this is what's one-time series, you can watch these things all the time, depending upon what's the nature of your research. And this is a function of many, many things: soil type, slope, many geomorphic and geologic reasons why these things behave. And there's a lot of smart people looking at that. But basically, it tells you the nature of the geophysics of the ground, and InSAR is a big deal, and it gives you the answer of how these things, it gives you a snapshot of the terrain. It results in these small landslides, and there are hundreds and hundreds of these things in the north. Here's an example of these what is called retrogressive landslides. And in this case, I just want to show you that we use both Radarsat and the German satellites, TerraSAR, to make a more comprehensive time series map, a time series motion. A colleague of mine at CCRS was working on active rock slides in the area in Gaspésie, where the main railway line is being impacted by this big rock slide, and he's able to produce these InSAR motion maps. And this shows the dots show the type of motion. Now this area is vegetated. So I was involved in the study for a bit. We were able to put what is called corner reflector, which is like a mirror, that the signal goes to this mirror, so to speak, goes back to the satellite. And you can see the motion pretty accurately because the vegetation shakes and it decorrelates your signal. Without going into a lot of detail of decorrelation and if you like, good signal mapping using corner reflector, it just showed these are the techniques we can use to get accurate InSAR measurement. Okay, I just want to go through quickly so we have time for questions. Here, an example where homes are falling into the ocean in Newfoundland, and we use InSAR measurements to look at time series, to look at the soil erosion and the coastal erosion, as well as groundwater flux that created this motion in Newfoundland. In China, we were helping the Chinese in Tibet to look at land motion in their particular part of the world. Canada was helping them and to look at land motion. Here's our InSAR map. The red shows areas of motion. And I also want to show you these houses, these homes. They're very big and beautiful homes. They were used as corner reflectors. So we use our radar to calibrate our signal, and the landslide was occurring in here. Just quickly taking you various parts of the world. In India, we use again the InSAR, again sticking with infrastructure in the Himalayas. In the upper Himalayas and Indian Himalayas, these slopes are really moving on these strategic highways. Here, the folks living on top of there, they're moving. All these areas are moving, and as the monsoon getting larger and so forth, a lot of motion going on, land motion. This is how it looks like. The red are the motion. All these villages are being impacted by the motion. I hope not. One of these days, they may just fall into they may be affected by this land motion, and we keep our fingers crossed. In hurricane, I think it's called one of the larger hurricane in the Bahamas and the Caribbean in Dominica. This was mapping the land before and after the hurricane. And that shows soil motion of the landslides before and after. All these areas are moving and impact these coastal communities in Dominica. As a matter of fact, I have a PhD student at the University of New Brunswick. She's finishing her PhD in the Caribbean, looking at hurricane motion and landslides and so forth. Hopefully very soon that work can be done. This is one of our slides. Oil slicks is a big deal for RCM. The black area shows the oil slick. These are the platforms. A lot of new studies are being done on the type of oil. And the kind of studies being done is basically what they may call areas that's similar to oil slicks. They call them lookalikes. Could be a very quiet, smooth waters. So one has to be very careful if these are actually oil slicks. Carefully, if they're near a platform, they're obviously oil slicks. So Radarsat is good for that. In Guyana, a lot of mining where you have placer mining affecting these small rivers. You can watch them over time with radar imagery before and after. And the country, the mining department can see who is stealing the gold from these placer deposit, whether they're permitted to be there or not. Just a quick view of some of the infrastructure work. Coastal motion. A lot of work is being done on accumulation along the coast. Geographers all over the world are interested in sea level change and accumulation in erosion in the tropics all over the world. Here's a radar imagery that tells you these things fairly well over time. CCRS have done some good work on using radar and flooding in Montreal, Ottawa here a couple of years ago. And just shows you the trajectory, the satellite data at 6:30, 6:35. So my colleagues have done it, 7 o'clock, they go to CCRS, the scientists, they produce a map by 10:30, for the mayor and city of in Montreal or in Gatineau or what have you. Very good late information on flooding using RCM data. Mapping faults, very easily done from radar, but now the future is looking at the polymetric scatter. And what that means, you can map more faults. And if you map more faults on the Canadian Shield, you're going to find more mines. That's the message. Radar is good for fault mapping, integration, more faults from RCM equal more mines. That's the message here. Now we can look at these slopes on a daily basis using InSAR. My colleague at CCRS have done this, from February the 16th, 18th, the 22nd, 24, and so forth. In just 2 weeks, he was able to see how that slope is moving. In this area in where you have the CNR in the Thompson Valley in BC, where he was looking at how these slopes are affecting the CNR, CPR. And what the point is that very rapid soil motion in these areas. What the future now in the Arctic? Let's start with the Arctic, end with the Arctic. A lot of rock, the scatter of these rocks are different because of texture, the radar texture. You can map them very easily and in the Arctic, and the implication of these as it results can have a lot of implication in Mars geology. So I just look at the Perseverance. I just looked at some slides the other day, cut them out and put it here. All the message I want to say, what we understand from radar backscatter in the Arctic for lithologic mapping can be applied to planetary geology. The sense of the rock texture, the breakage, the faults, the impact structure, the alien features, all of these, the science of the Arctic can be applied to Martian and planetary geology, the kinds of science we understand there. I want to talk to the people who do hyperspectral remote sensing. What they have done in hyperspectral, they were looking at signature of various rocks. Well, that's old science. And they did a lot of good work in finding mines, looking at hyperspectral signature of rocks. The new science of radar remote sensing, that's old, this is new, is that we can look at a polymetric scatter from RCM in the high Arctic. And here are two examples of the polymetric signature. That's the future, to look at polymetric signature of the high Arctic, which can apply of these large impact structures in the case of Houghton crater in the north. This is an example, can be applied to the planetary geology, the kinds of science we do in the high Arctic. That's how it looks like in the high Arctic again on the Houghton crater. What we learn here, it's called a Martian analog, the NASA, the Geological Survey, McGill folks, I think University of Ottawa folks, I think, are all working on the scatter of data and the mapping for planetary geology. Okay, what I want to leave you with. Radarsat Constellation Mission, it's provide a global radar. It provides some a global radar information, continue from Radarsat 1 to an RCM. So we are still doing a lot of good work in Canada and externally. In my case, this is only one example. Interferometry is going to give us a lot of information on processes. And we need geographers to help us here in a big time, from image processing, geomatics, geomorphology, and land use planning. There's a huge need for highly qualified young people, PhD, masters, professors, to help these folks. And there are many, many questions. InSAR, time series science, as we look at climate change processes, polymetric signatures, looking at all kind of target from ice to rocks to infrastructure and so forth. And so there's an open science and lots to be done. I just published, I edited a book which came up just last month in January. The Advances of Remote Sensing for Infrastructure Monitoring was published by Springer. It's not cheap, but I think university you'll probably get it at a half price, I'm not sure. And so infrastructure and radar is close to my heart. And I just want to leave you there. And I want to show off our RCM. And this is the last day of RCM on Earth in June 2019. That's my pretty face. Thank you. I think, I don't know, I think I got, maybe 7-8 minutes for question. But if the chair wants, maybe you can go on a little bit beyond that. So
yes.
Thank you again. So I would
you.
leave it up to you folks to take it over.
Thank you, Dr. Singhroy. That was a great presentation, very informative. We have one question here in the chat. I'll read it to you. It's from Anis. He's asking, what kind of timeline should students expect if they want to access RCM data? how fast is the approval process?
Oh, I don't know. Short answer, I don't know. The approval, I'm not in the government anymore. Or the approval process for a student to get radar data. Okay, what I would do, like, I don't know the answer for that. I think I will call the director, student, pick the phone up and call the director of the CCRS. Tell them you want RCM data. The answer would be yes, because they want to help you out for sure. And it's not a she, he will tell you how to get the data quickly. So him or her, the student, I don't know, I'm not with the government anymore, but it would be quick, I would hope. You remember, tell us, what's the person name?
Who was asking?
Yes.
It was Anis.
Anis, call CCRS, they'll tell you, and they will give you data, but go through CCRS.
Thank you. Do we have any other questions? People can turn on their microphone if they want, or write it in the chat.
I just want to mention Luke, I guess, Luke and Trudy just replied in the chat that says it takes just a few days.
Oh, there you go.
So that sounds good.
You got your answer there, yeah. And if you want the data, I would, and this is just because I used to work at CCRS. First, depending if you want the data for ice, oceans, land application, and so forth. First, find the name. This is an inside track information. Find the name of the scientist at CCRS who is working in, urban or ice or whatever. You talk to them first before you talk to the director. I hope the director is not online. So talk to the scientist first. Then you'll get the real stuff and they'll tell you exactly what they got. They'll tell you the image, they'll tell you the quality, and then get the scientist actually to get you the data before you talk to the director. That's an inside track. You owe me a coffee for that one.
I have a question, actually. You talked about stable reflectors.
Yes.
Do you have to use those? And I guess my other question would be, if you're working in a very remote area where there's not a lot of large known to be stable targets, would that be a limitation for InSAR applications?
Yes, ma'am. Okay, this is very remote. This is in Tibet, okay? And yeah, two things. Go back one. Okay, here is our coherent reflector. That's what a coherent reflector is usually used when you have a lot of vegetation. So that's because the vegetation moves a lot. The wind blow it, and therefore, if you're looking at, I'm just going to very simple explanation here. If the wind is blowing and you want to look at centimeter motion, you need to have like a mirror, like a reflector on the ground, and you can build your own. Now the folks are building their own, but you can get it if you want to buy it. They're about, I don't know, a company in Newfoundland, Memorial University. They sell these things about $1,500 a piece, I think. Don't quote me on that, because call them on it's like a mirror. They have what is called a Trihedral Reflector, and you put that in the vegetated area. And the reflector moves, the ground moves, so to speak. But when you're and we do this a lot in Canada. So that solves it because we use reflector, even in the Arctic pipelines and so forth. But when you are in Tibet now, and you don't have reflector, you have to use a background, and the houses are a background. So you train your radar, because this is not moving, and the ground move relative to this. So that was the first question. You need reflector, and the second on the remote areas. And the second question was?
Well, I was wondering if the application of InSAR in remote areas where there aren't a lot of very reflective
Yes.
stable targets, would then, if it would be possible to use InSAR for ground
Yes,
movement.
they are. The way we get around that is using reflector. But there is the short answer is yes and no. If you have a lot of reflective target, you're good.
Mm.
Like if you don't have, like if you're doing this in the Amazon, let's say, then you would, or the dense forests of the Canadian, the boreal forest, then you need reflector, or the Amazon. But most parts of the world, you can find reflectors.
Right. Like a bare mountain, for example.
Yeah, bare mountain, a bare rock, and you can use those to help you out. Remember, you're dealing with 2 or 3 millimeters of motion here. You got to be, you got to be on top of your game here. You got to be very accurate. So those are good questions. And I think, I don't know, it's up to you. I think we're
it's
there
1
on.
o'clock.
We're good.
So do we have other questions quickly if people don't have to leave right away? Oh, yes, Karina.
Thank you for your presentation. I'd just like to mention that like every day there's like so much satellites that are released into space, and it creates space pollution, right? And that also creates issue in terms of like satellite collisions, right? So I was wondering, what's your opinion on that issue?
Well, the satellite doesn't collide. They're not like a highway.
I mean when there's like so much,
an airplane. They're like airplane. They don't hit one another. Okay, I'm sorry. Yeah, they don't collide.
Sorry, I mean like there's like so much satellites released every day, and like we keep on hearing that like there's like about some days 90 satellites are released per day in the world.
Correct. Yeah, that's correct.
So
you're right.
I feel that creates issues in terms of satellite collisions, right? So wouldn't that be an issue, or?
Yeah, well, the issue is download of information. I don't think it's only when they, so when they blow up, you have space debris and all that kind of thing. But is there an issue of having too much satellite? That's your question. No, because I'm a satellite guy. The more measurement you got, the more better it is. What I think we need, Karina, is we need to coordinate. It's like if Europe is putting on some satellites to do various things, then we do not duplicate what they're doing. I think that committees nowadays, it's called CEOS. I forgot what is the term in Committee for Earth Observation. There's programs where there's coordination. But I agree. We in remote sensing, we need a lot of information to understand the geophysics of the Earth and the processing of the Earth, whether it's climate, hurricanes, Arctic melting, ice dynamics, and you go on and on and on. And there's a lot of modeling and field work is doing, and the satellite data confirms or do not confirm what we are measuring. So from a modeling, climate change, that kind of, we need satellite data and we need more data. But what we need to do is to coordinate who is collecting the data and where they can share. No, the Indians, the Americans, the Canadians, Europeans, Germans, and so forth. We need to see what they're doing, and then we don't want to duplicate what they're doing. But I think one satellite colliding with the other, no. It's like 2 airplanes that not collide. They're in different orbits, so to speak. It's a problem, but it's not a problem, depending on where you stand. Okay.
Thank you. So I think that's it for us today. So we can turn on our microphones and give a good round of applause for Dr. Singhroy. Thank you.
Thanks again. Okay, I'm happy to do it. Happy to do this, and thanks to Anders and others too.
Thank you. And there will be 2 other seminars in March and April. So hopefully a lot of you join us again in April and March. Thank you.